Hello guys, I'm here again, Engineer Jewel Ryan Nicole Viriosa. So, for today, our topic is Fundamentals of Algebra. So, let's start. So, again, we have to set our objectives. Our learning objectives for today is understand the fundamental principles of algebra. Of course, we need to understand it upon finishing or watching this video, and then apply the fundamental laws and theories related to algebra in solving mathematical problems. So algebra, it is really related to mathematical problems. So I hope you can apply what you will learn in this video sa mga mathematical problems that you will encounter in the future, and then identify the different properties of number system. So I will be discussing different number components of number system. So let's proceed. So first of all, I want you to introduce to some key terms that we will be encountering here. So algebra. Algebra is a branch of mathematics that substitutes letters for numbers. So back when in elementary, we are using simply 5 plus 3 is equals to 8. And then here in algebra, we have, for example, x plus 3 is equal to 8. So meaning our x is equal to 5. So algebra is a branch of mathematics na we substitute letters for numbers, and then it is mainly about finding the unknowns or putting real life variables into equations and then further solving them. And we also have this what we call algebraic equation. So algebraic equation, as you can see in one of our key terms here, is a scale where it represents a scale where what is done on one side of the scale is also done to the other number or the other side of the equation. So we'll be encountering that in the future more. And then as you can see, the picture here is the reason why algebra exists. So he is Abu Jafar Muhammad and Musa al Khwarizmi. So I've been searching on how to pronounce his name, but then I failed to search it. So he is a mathematician, astronomer, geographer, and then he is the reason why algebra is existing now. So, of course, we must know also what is the main uses of algebra. So, algebra is widely used in many fields, including medicine, accounting, of course, engineering, architecture, but it can also be used in everyday problems that we are encountering. It also develops critical thinking, and then inductive reasoning. So understanding this will help us or other people be better on handling problems. So algebra is the etymology of the word algebra. So I hope you got something from those key terms. So let's proceed to the next slide. So here we have number system and its properties. One of our objectives today is to identify the different properties or identify the different components of number system. So let's go. Let's start let's start with natural numbers. What are those natural numbers? So natural are, we also refer this as counting numbers. Of course, counting numbers, these are the numbers 1, 2, 3, 4, and 5, etc. and so on. And then of course, there are infinitely many natural numbers. Sometimes these natural numbers are denoted as N, big letter N for short, because it is too long if we put only if we put it as the word natural or counting numbers. The whole numbers are the natural numbers together with 0. So again, whole numbers are natural numbers with 0. And then natural numbers are counting numbers which are 1, 2, 3, 4, 5, etc. and so on. So next up we have integers. So integers are the set of real numbers consisting of the natural numbers, their additive inverses, and 0. Again, integers are set of real numbers consisting of the natural numbers, their additive inverses, and 0. Okay? So let's proceed to another component of number system. So this is the rational numbers. Rational numbers naman are those numbers which can be expressed as a ratio between two integers. So again, rational numbers are those numbers which can be expressed as a ratio between two integers. So you can see the pattern now, no? So again, next. So next, what's next? Irrational numbers. So if we have rational numbers, we have irrational numbers. And then we have the real numbers. Real numbers, our rational numbers and irrational numbers are under our real numbers, which is, as defined, real numbers is the set of numbers containing all the rational numbers and all of the irrational numbers. The real numbers are all the numbers on the number line. So if you encounter the number line, all the numbers there is real numbers. And then we have one more, real numbers. And then if we have real, we have imaginary numbers. And then of course, above all of them, we have what we call complex numbers. This includes the set of real numbers, imaginary numbers, rational numbers, irrational numbers, integers, and natural numbers. So our complex numbers composed of two major components, the real numbers and imaginary numbers. And then our real numbers is composed of two other components, which is rational and irrational numbers. And then rational numbers have subcomponent which is integers, and in natural numbers is under integers. So we have here somewhat of what we call diagram of the number system and its properties. So let's go now with the divisibility and factoring. So we have three major terms here that is quite related to divisibility and factoring. So prime numbers. What are those prime numbers? A prime number, or sometimes it is called a prime, is a natural number which has exactly two distinct natural number divisor. So what are those divisors? That is 1 and itself. So for example, 2. So those divisors are 2 and 1. And then 3, the divisor is 3 and 1. 5, the divisor is 5 and 1. So we have 7, 11, 13, 17, 19, 23, 29, and so on and so forth. And then, by definition, 1 is not a prime number. So, we go to factoring. So, if a number can be expressed as a product of two or more whole numbers, then those whole numbers are called factors of that number. So, for example, we have number 6. So, the factors are 6 and 1, 3 and 2. So, again, the factors of 6 are 1, 2, 3, and 6 because 2 times 3 is 6 and then 1 times 6 is 6. So, again, a factor is any number that will divide into another number exactly or with no leftover or remainder. Example, 8 can be divided by 2. So, the factor in this example is 4. 2 and 4 because 2 times 4 is 8. But it is not necessarily that the only factor is 2 and 4 because we also have 1 times 8 is equal to 8. So, our possible factors is 1, 2, 4, and 8. And then, we have other term here which is multiples. So what is a multiple? For example, you are asked what are the multiples of 7? So the multiples of 7 or the multiple of a number is the product generated when that number is multiplied by an integer. So for example, what are the multiples of 7? The multiples of 7 is 7 times 1, 7. 7 times 2, 14. 7 times 3, 21. So those numbers are multiples of 7. So I hope you understand the prime numbers, the factoring, the multiples. So let's go to the next. So before we proceed to the test of divisibility, another topic, I will just provide more examples of factors. So for example, factors of 24, 1 and 24, 2 and 12, 3 and 8, and then 4 and 6. So next, factors of 27, 1 and 27, 3 and 9. And then factors of 56, we have 1 and 56, 2 and 28, 4 and 14, and then 7 and 8. So factors of 61, 1 and 61. So again, numbers that are greater than 1 and has only 2 positive factors, 1 and itself, are called prime numbers. So we have here now the test of divisibility. So I included here the divisibility of 2, 3, and 5. So a number is divisible by 2 if the last digit is 0, 2, 4, 6, or 8. So meaning, it is divisible by 2 if the last digit is an even number. So as an example, 2,346 is divisible by 2 since the last digit is 6. So in general, 2, 3, 4, 6 is an even number also. That's why it is divisible by 2. So next divisibility rule, divisible by 3. A number is divisible by 3 if the sum of the digits is divisible by 3. So we have an example here. 23,457 is divisible by 3 since the sum of the digit is 21. So how do we solve the sum of those digits? So we have 2, 3, 4, 5, and 7. We get the sum of this. We arrive at 21. 21 is divisible by 3. Therefore, 23,457 is divisible by 3. Lastly, divisible by 5. A number is divisible by 5 if the last digit is either 0 or 5. So, we have a lot of digits here. So, this is 1, 2, 12 billion, 457,896,535 is divisible by 5 since the last digit is 5. No matter how many digits is that, as long as the last digit is either 0 or 5, that number is divisible by 5. So, we have here prime factorization. So, prime factoring is to factor and then continue factoring a number until you can no longer reduce the factor into constituent factors any further. So, prime factoring is continuous factoring. Any number can be written as a product of prime numbers in a unique way. So, we can break up a number into its prime numbers. So, the process is called prime factorization. So, for example, to write 60 in prime factored form, we will get 60 is equal to 2 times 2 times 2 times 3 times 5. Or we can further simplify this to 2 raised to the cube power, or 2 cube multiplied by 3 and then 5. So we have I can suggest two major steps here. So first, if you want to prime factor something or a number, choose the smallest prime number that will divide evenly into the given number and then divide it. So repeat step 1, since prime factorization is repeated factoring or continuous factoring until the final answer is a prime number. So for example, here in 60, the smallest prime number that will divide evenly to the given is 2. And then, actually, you can use any prime number available. You will be arriving at same answer naman, since there is only one, since we are using prime factors naman. So, we will be arriving at same answer here in prime factorization, whether you factor first, use factoring. For example, you use the factor of 60 2 times 30, and then you first use 5 times 12. At the end of the solution, your answer must be 2 times 2 times 2 times 3 times 5, or 2 cubed times 3 times 5. So I hope that is clear. So here's a specific example of what I am suggesting kanina. So find the prime factorization of 24. So the smallest prime number that can divide 24 is 2. So 24 divided 2 is equal to 12. But 12 is not a prime number. So we need to factor it further. So, factor further, 12 divided 2 is equal to 6. Again, 6 is not a prime number. So we need to factor it further. 6 divided 2 is equal to 3. And here we have 3 as a prime number na. So, our final answer is the prime factorization of 24 is 2 times 2 times 2 times our last prime number, which is 3. So, simplifying this is equal to 2 cubed times 3. So, other terms na related to our topic today is greatest common factor, and the other one is the least common multiple. So, first, the greatest common factor. So, to find the GCF of a set of numbers, you must factor each of the numbers into primes. Then, for each different prime number in all of the factorizations, do the following. So, here's my suggested method. So, first, count the number of times each prime number appears in all the factorizations. And then, second, for each prime number, take the lowest of these counts and write the result. Lastly, the greatest common factor is the product of all the prime numbers written down. So to visualize this, I will be presenting an example. So, find the GCF, or the greatest common factor, of 72, 90, and then 120. So, first step, we have to determine the prime factorization of each number. So, we have here, for 72, our prime factorization is 2 cubed times 3 squared. And then for 90, we have 2 times 3 squared times 5. And then for 120, we have 2 cubed times 3 times 5. And then second step, take the prime numbers that appears in all the factorizations. But remember, taking the lowest number of times they appear. So, the prime numbers that appear in all the factorization for 72, 90, and 120 is 2 and 3. So, take note, take the lowest number of times they appear. So, lowest number of times they appear, 2 appear once in 90 and 3 appear once in 120. So, our greatest common factor for 72, 90, and 120 is 2 times 3, which is equal to 6. So, here's our last topic for today, the least common multiple. To find the least common multiple of a set of numbers, you must factor each of the numbers into primes. Then, for each different prime number in all of the factorizations, do the following. So, many of you, or even me, ay nalilito sa least common multiple and greatest common factor. So, here's my suggested steps on how to do this. First, for the least common multiple, count the number of times each prime number appears in each of the factorizations. So, meaning you have to prime factor it. And then second, for each prime number, take the largest of this count and write the result. Third, the least common multiple is the product of all the prime numbers written down. So, to visualize this, another example will be provided. So, here it is. Find the least common multiple of 16, 24, and 40. So first, again, determine the prime factorization of each number. So for 16, we have 2 raised to the 4th power. And then for 24, we have 2 cubed times 3. And for 40, we have 2 cubed times 5. Second, take the prime numbers that appears in all the factorization. So remember, in GCF, we take the lowest number of times they appear. So that's the difference. For LCM, we take the highest number of times that they appear. So, final answer, LCM for 16, 24, and 40, we have 2 highest number of times that it appears is in 16, which is 2 to the 4, and then 3, it appears once in 24, and 5 appears once in 40. So 2 to the 4 times 3 times 5 is equal to 240, the LCM of 16, 24, and 40. So I hope you learned today. So, if you wish to have a copy of this PowerPoint presentation and complete module of Fundamentals of Algebra, kindly email me at ryannicole05@gmail.com. Thank you and keep safe.